All right, everyone. So, the last several videos we focused on the second order linear homogeneous, differential equation with constant coefficients. We saw every case that the characteristic equation solution could have, and based on that, what our general solution looks like. Now, this time today we're gonna extend it. We're gonna see, how to solve any nth order linear homogeneous ODE with constant coefficients. So to do that, let's first write what our ODE is gonna look like. So as I showed before, in some coefficient nth derivatives, it's the nth order linear homogeneous ODE. So that let's say n minus one y. Now these are the derivatives. These are not y to the power of n or anything. These are the nth and nth minus one derivatives. Now it goes all the way up to the zeroth a, okay, and the zeroth derivative. Well, that's just y itself. So this is gonna be equal to zero. Now this is my, and all these constants a, a sub 0 up to all the way up to a sub n, they're all constants. Okay, they're all constants. And also we need to note that a sub n, for this to be nth order, nth order, this cannot be equal to 0. This cannot be equal to 0. All right, so I'm going to go about discussing this step by step. All right, so we have this nth order OD. This is gonna actually give us, using the same substitution that we did, I think, a few videos back, like you know trying out the solution y is equal to e to the power mx. Okay, this is actually gonna give us an nth degree polynomial. Okay, the characteristic equation, it's gonna look something like this. Okay, so actually I'll scroll up a bit. Okay, so the characteristic equation is gonna look something like this: a sub n. So you have the nth derivative of y, replace that with the nth power of m. Okay, you have the n minus 1, you have the n minus 1 derivative, you replace that with m to the power n minus 1, all the way up to a sub 0. Then y is the zero derivative, that's why it's just m to the power 0, which is just 1, so no, don't need to replace that with anything. So just a sub 0. Now this is equal to 0. This is my characteristic equation. Okay, this is my characteristic equation. Now what's important here to note is that our characteristic equation, the degree, it's a polynomial equation, right? And the degree of this polynomial equation is the same as the order of our differential equation. So this is the characteristic equation is an nth degree polynomial equation. What does this tell us? Now, if you remember the fundamental theorem of algebra, any nth degree polynomial equation is gonna have n roots. Okay, it's gonna have n roots. Okay, if you're also counting the repeated roots, any repeats that a root may have, if you're also counting them, okay, altogether you need to have exactly n roots, the same as the degree of your polynomial. Okay, now we also know that since this is an nth degree polynomial, since this is an nth degree differential equation, this must have the general solution. Okay, the general solution, you must have n arbitrary constants. You must have n arbitrary constants in the general solution. Okay, so your characteristic equation must have n roots. It has n roots, and your general solution of your differential equation, that has n arbitrary constants. I think you see where this is going. Every root, okay, even the repeats, okay, even the repeats, every root contributes one, and exactly one arbitrary constant to my general solution. So if you have one root, if you have a root, okay, this one root will contribute, okay, or it's going to supply one and exactly one arbitrary constant to my general solution. So one root translates to one arbitrary constant, Now, keeping that in mind, we're actually going to see what are solutions for all the cases that the roots may have. Okay, now let's start that. The first case, and this is the simplest one, is Okay, so if we have suppose say some root, let's see, I'll call that r. Okay, some root r. Okay, now this is a, let's see, distinct. This is a distinct. Okay, that means it's, it only occurs once, so it's a distinct real root. Let's say we have a distinct real root. Okay, and it's r. All right, now this is, and you can prove it yourself really easily. It's really the same process as we did with the second order differential equation, when we dealt with the distinct real roots. This is exactly the same thing. Okay, every root, for every root, this one root, okay, this, if you're talking about this one distinct real root, it's gonna contribute this sort of a term. Okay, now we this is going to be, since this is a root, as we know, the initial assumption, the initial function that we try to plug in here to find the solution is e to the power mx. Now here m is equal to r. Obviously it's a root, so our solution from this root contributes a solution of e to the power rx. Okay, the root is r, so e to the power rx. We also know that since this is a homogeneous equation, you can multiply a constant with this. Okay, you can multiply a constant with this and it's still gonna be a root. Okay, so every distinct real root, distinct, okay, this we need to keep in mind. Every distinct real root contributes a term like this. Okay, some constant multiplied by e to the power that root multiplied by x. Okay, so the important thing is, and now I'll actually make a table here. This is pretty important. So on the left, I'm gonna have, let's see, the root. Okay, the root, and on the right I'm gonna have the solution. Okay, the solution that those roots, okay, or root supplies, okay, or contributes to. Let's say if you have k, okay, if you have k distinct, okay, k distinct real roots. Okay, now we need to keep in mind all these terms that we're introducing here. All of these roots, they're obviously real. Okay, one thing is they're real. Okay, and also they only occur once, each one of them. Okay, they only occur once. Okay, now if you have k, k of such roots. Okay, k is any number, so you have k such roots. Okay, your the solution for this portion, this whole portion, these k roots provide a solution. Okay, portion of the solution like this. So you have, it's just for every root you're gonna have this term. Okay, it's for every root you're gonna have this term. So if your roots are, you have k distinct real roots. So if, let's say, r sub 1, r sub 2, all the way up to r sub k, all right, now the root, as we discussed, the root that r1 is going to contribute is gonna be c sub 1 multiplied by e to the power r sub 1. Same process for r2, same process for r2. It's gonna contribute c, some constant c2 multiplied by e to the power r2x, and this is gonna continue, and your kth root, okay, r sub k is going to contribute something like this. Okay, to your solution. So this is r sub k. Now, as we discussed, about the solutions of linear homogeneous differential equations, if you have, some roots, and if you take the sum of them, if you take their sum, that sum, this whole thing is also root. Wait, have I been saying root? Anyways, if you have a bunch of solutions, yeah, this whole thing is also gonna be a solution. Okay, so this is the portion of the solution. Okay, that these k roots, okay, these k roots all together contribute. Okay, now there's one really important thing that we need to see and make sure of. Now I'll just focus on the number of roots. Okay, so we have k roots. Okay, we have k roots. This should contribute k arbitrary constants to my general solution. Now let's see if that's the case, and it indeed is. We go from c1 all the way up to ck, c sub k, right? So there are indeed k arbitrary constants here. Okay, and that's why this what we are doing here is valid. Okay, so this is this. So if you have k, okay, if you have a number of distinct real roots, okay, this is how you find the part of the solution for them. Okay, so find the solutions individually in this term. Okay, some constant multiplied by e to the power our root, okay, into x. Okay, and this term you repeat that for you do that for every root, every real root. Okay, so let's move on. So that's one case done. Now let's talk about if you have repeated roots. Okay, if you have repeated roots. Now, unlike when we're only dealing with the quadratic, root could be only repeated twice. Okay, a root could be only repeated twice. Now our root might be repeated even more times. So suppose, say, I have a root. Let's call that p. Okay, I have a root p. So let's say m is equal to p, m is equal to p. So, and this root is repeated k times. Okay, it's repeated k times. Uh, repeated k times. All right. Formal, it's called said that the root p has multiplicity of k. But anyways, I won't go too much into that. So if your root is repeated k times, let's actually try to do the same thing that we did when we had this is second order differential equation. So definitely this is gonna be a root. This is gonna be a root. E to the since m is equal to p. Now this is a valid solution of our characteristic equation. This has to be a root. E to the power p e to the power px. This has to be a root. Now let's modify that a bit. Okay, so if I have e to the power px, now I'll still have that, and I'll also multiply an x here. Okay, now that's also let's again modify this a bit. Okay, so e to the power px. This time I'm gonna raise the power of x by another one. So, and this is gonna we can keep doing this, but for how long? Okay, that's the question. I think you can see where I'm going with this. It's really the same the same procedure with the second order differential equation. All of these are actually individually roots of our differential equation. All of these are individually roots. Okay, so, and if these are roots, I can also multiply by some arbitrary constant here, some arbitrary constant here, some arbitrary constant c3 here. Okay, and I'm gonna take their sum. I'm gonna take all their sum. The question is for how long. Okay, how many times am I gonna do this? Okay, now for that we just need to see how many roots there are. Okay, now if you're counting all the repeats individually, you have k roots, right? This one root is repeated k times. Okay, and the in the language of the fundamental theorem of algebra, we do have k roots. Okay, counting the multiplicity, we do have k roots. That's why this portion of the solution, this solution that's contributed by the this m equals p repeated k times. Okay, it must have k arbitrary constants. That's why c1, c2, c3, we are gonna continue this up to c sub k. Okay, and we're gonna have also e to the power px here. The big question is actually I should have written that. Okay, the big question is what's gonna be the power of x here. Okay, how much do we go with the power of x? Now to do that, we just need to make a small observation. It's c1 e to the power px. It's actually c1. You have x to the power 0. Multiplied with this. It's just implicit because it's just 1. Okay. Now if you also notice c2. Okay, here you have 2. The power here of x is 1. Here you have a 3. The power of x is 2. Now I think you see the trend. If you go up to the kth coefficient, c sub k, the power is gonna be 1 less. Okay, so you go up to x to the power k minus 1. X to the power k minus 1. All right, now that's interesting. One thing we can do, again, the same thing we did before, we can actually factor out e to the power px. We can actually factor out e to the power px. Okay, and if you do that, what we have is c sub 1 plus some constant c sub 2 x, x, just x. Okay, then some constant c3 multiplied by x squared, all the way up to my kth coefficient. the same number as how many repeats there are of the root. So the kth coefficient, the power of x is gonna be 1 less. Okay, the power of x is gonna be 1 less, and all this is multiplied by e to the power px. So p is that repeated root. Now, okay, the way I remember this is not like this formula. Well, most of it is, but the way I like to remember this is, you have e to the power px, obviously you have e to the power px. This is gonna be multiplied by, a general k minus 1th degree polynomial in x. Okay, k minus 1th degree polynomial. Okay, polynomial. Okay, so our exponential is gonna be multiplied by, okay, and a polynomial whose degree is 1 less. Okay, this is really important here. This is really important. We need to remember this, that polynomial degree of that polynomial that we are multiplying by, the degree is 1 less. The degree is 1 less than how many times this root is repeated. How the multiplicity of this root. All right. This is how we deal with repeated roots in general. Now we just have one case left. I'm pretty sure you can guess what that is, and that's when you have complex roots. Okay, and again, it's a lot similar to what we did with the second order differential equation, but there's one very key difference here. There's one very key difference here, and that is that when you had a second order differential equation, if you had one complex root, the other one, okay, had to be its conjugate, and you can only have two roots there. Okay, so your complex roots couldn't be repeated. Okay, your complex root couldn't be repeated. But now you actually can. Let me write all this stuff down. Okay, so our complex roots. Okay, talking about our complex roots, they can actually be repeated. Okay, so complex roots. Okay, now we are actually allowed to repeat them. So they can be repeated. Okay, now what does that imply, or how what's the major change due to that? Well, if that's the case, one thing I just want you to look at this to see, if you have suppose say 2 plus i, and this is repeated 5 times. Okay, this is repeated 5 times per se. Okay? Just an example. Okay? So this is a root to our characteristic equation. It's repeated 5 times. If that is the case, it's not just one thing. We're assuming that our coefficients of the differential equation and also the characteristic equation is they're all real. Okay, they're all real. If that's the case, not only will you have the conjugate as the rule, as another rule, we do know that the 2 minus I has to be a root. Since coefficients are real, the conjugate also has to be a root. Now, not only does it have to be a root, it also has to be repeated the same number of times as this one is. So if this is repeated 5 times, this also needs to be repeated 5 times. It's pretty important. This also needs to be repeated 5 times. And altogether you have twice the number of roots. Okay, you have twice the number of roots. So if that's the case, in general, suppose say you have a complex root, okay, lambda plus mu y. Now you're also gonna have conjugate as the root. And by the way, I'll already mention this, but you might think, okay, so we're dealing with when the the complex roots are repeated, but what happens if they're distinct? Well, that's that's just a special case of this, when we're repeating this just once, and it's really the same form as what we did with the second order differential equation, so there's nothing new there. Anyways, so if suppose say lambda plus mu y is repeated k times, okay, it's repeated k times, lambda minus mu y has to also be repeated k times. And altogether, this is one thing we really need to be careful about. Altogether, we have 2k solutions. Okay, 2k solutions, 2k solutions of roots, or k pairs. Okay, 2k things. You can also say it's k pairs. K of this, k of this, k of that. So you have k pairs. Okay. Now the important thing is, more than the k pairs thing, is actually that we have 2k roots. Okay, 2k solutions of roots. Well, when we derive the solution here, we know for a fact that there has, we need to have 2k arbitrary constants. If you have k pairs of, of a complex. So let's write that down. Suppose say the root, suppose say the roots. Okay, so m equals lambda plus or minus mu. As I said, they need to, they come in pairs. Both the conjugates are roots. Okay, so if that's the case, if suppose say m equals lambda plus or minus mu I, you have k pairs of them. Okay, you have k pairs of them. So you have k pairs. It's k pairs. So altogether 2k solution or 2k roots. Okay, I'll also write that down. So altogether, 2k roots, 2k roots. Now, what's gonna happen here? What's gonna happen here? Now, it's the same thing, and again here there's one thing and I'd like to mention. So you can actually use the same form as these to derive this formula. Okay, we didn't strictly actually bound these to be, well, these we do use, this is the simplest form. Okay, when we have these cases, but you can also use these, okay, to derive what happens here. Okay, so anyways, I'm thinking I'm blabbering too much. So the thing is, suppose say if lambda plus mu I, okay, it's repeated k times. Okay, it's this one, lambda plus mu I is repeated k times, lambda minus mu I is repeated k times. So let's first deal with only lambda plus mu I. Okay, so as we know, it's repeated k times. We're gonna do the same thing here. We're gonna use the same logic here. Okay, so we have lambda plus e to the power lambda plus mu I. Okay, suppose say the coefficient is a sub 1. Okay, then we this is gonna be repeated k times. So second, this also we need to modify this a bit. Then again, actually, why lambda plus mu I? It's lambda plus mu I multiplied by x, obviously. Okay, so we need to modify this a bit, multiply by x, then again lambda plus mu I, okay, multiplied by x, all the way up. We need k of these arbitrary, a's, okay, arbitrary constants. Since we have k solutions with lambda lambda plus mu is repeated k times. Okay, so this is gonna go all the way up to same thing, exactly the same thing as we did here, because just replacing the letter and all. It's gonna go up to a sub k, x to the power, well, 1 less, it has to be 1 less, and this is multiplied by, again, same thing, it's a repeated root. Okay, so now this is for lambda plus mu. Same thing is gonna happen for lambda minus mu. We also have that part, that other side of the bridge. Okay, so lambda plus mu, you also have lambda plus mu is also repeated k times, as I've already mentioned. So let's say it's b1 e to the power lambda minus mu I x, okay, plus some constant b2. Need to modify that a bit, multiplied by x. It's power lambda minus mu I multiplied by x, all the way up to okay, so b sub k, the same thing as we're doing here, just with different letters and the different root. Okay, so x to the power k minus 1 e to the power lambda minus mu I x. All right. Now, something really fascinating and important happens here. So I'll actually do it in a different color. So what happens here? Let's actually add, as I've already showed, all of these are added. Okay, but the main thing is, let's actually add these, these two lines. Okay, they're already added, but let's see what happens if we simplify them. Okay, we can actually do a pretty neat simplification if we add the terms column wise, like I've written here. Okay, could factor out. Actually, I'll actually not go into the full detail here, because we have done this before. I hope you remember. And suppose say we had in the case of the second order differential equation, when we have a e to the power, I actually used the letters p and q here, but anyway, same thing. We have, suppose say lambda plus mu, right? Actually, I use these Greek letters now because that's the way it's often done. But again, it really doesn't matter what letters you use. And then you have this. Actually, again, I'm forgetting to write the x's. Really shouldn't forget to write that. Really shouldn't forget to write that. Let me see if I've missed out on that anywhere here. No. Okay. We saw, a couple of videos ago, what can we do here? If this is the case, we can actually factor out e to the power lambda x, and inside what we're gonna have is some arbitrary constant. I'm gonna call that c, multiplied by cosine of your imaginary part mu, okay, mu x, and then again some arbitrary constant d multiplied by your sine term. Okay, so the same thing really happens here. So when you add these terms column wise, suppose say if I add these two, what I'm gonna get is e to the power lambda x, okay, e to the power lambda x, okay, and then in brackets you're gonna have some arbitrary constant. I call that c, capital C sub 1, okay, cosine of mu x, and then the sine term. So some arbitrary constant, called that d sub 1, sine of mu x, and this is going to continue. The only difference with the other columns is we also have some power of x, okay, which we can actually factor, so that doesn't really complicate things much. That's just going to sit outside. So I'll just draw a small partition here, you could say. Now for the next term, this one, pretty much the same thing. Also, you can the only thing is you can also factor out x, okay, with the e to the power lambda x. So now what you're going to have inside is again some constant, c sub 2, cosine, and then this your sine term, some to constant d sub 2 multiplied by sine of mu x, okay, sine of mu x. Now this is going to continue. I'll also draw a small partition here. But anyways, all of them are added. I definitely want to emphasize that fact that all of them are added. Anyway, so now this is going to continue. This is going to continue all the way up to this last term, right? So this last term is, we go all the way up to, okay, your last term is going to be, again, you're going to factor out at the x term, then you have e to the power something, lambda x, and then you have some constant, we call that c. So this is the kth column. This is the kth column. Okay, this is the kth column, and that's why this our constant, this c, it's the kth c that we have, c sub k. So this is multiplied by cosine of mu x, and then you have d sub k multiplied by sine of mu x. Okay, so this is in fact your solution. You can actually simplify this a bit more. Actually, there's something about this solution. Many people actually use it like this. Okay, so many people actually do prefer to use it as it is here. Okay, instead of tinkering with this even more than necessary. But you can actually even make it a bit more concise. Okay, what you can do is you can factor, you can see, as you can see, e to the power lambda x, because all the solutions be having the same real part, e to the power lambda x, it's a common factor of all of these terms. And actually factor out this whole thing, and also you can decide to group the cosine and the sine terms of these individual parts. Okay, you're definitely gonna have to care for the x, the x terms here. So doing all that, what you're gonna have, okay, where should I write it? I'll actually write it here. So doing all that, what you're gonna have is, I'll actually write the e to the power lambda x in front so that we don't forget it. Okay, now we're gonna have the cosine terms group. So this is gonna be cosine of mu x. Okay, and inside what you're gonna have, the cosines had, as we saw, the cosines, what are there, what are in front of them. Let's see. If other than the exponential, what we have, with this one it's c1, this one it's c2, and also x, so c2x, and this goes all the way up to c sub k, which is multiplied by x to the power k minus 1, So what we have here is c sub 1 plus c sub 2k, sorry, not k, x, all the way up to c sub k, okay, multiplied by x to the power k minus 1. This is basically something that we did a while ago. This is basically a general k minus 1th degree polynomial x. All right, so that's one good way to remember this. And same thing is gonna happen with sine. Okay, it's not very different, except instead of c we were using d for all the sine terms. So what we're gonna have here is some d sub 1, some constant d sub 2 multiplied by x, and all the way up to some some constant d sub k multiplied by, well, the power of x is gonna be 1 less than k. Okay, and this is gonna be multiplied by sine of mu x. Okay, sine of mu x. Mu is your imaginary part of your solutions. So sine of mu x, and all of this we are gonna enclose that in a big square bracket. All of this is multiplied by the exponential. All right, this is the most concise form. Okay, again, there's one thing, I actually, if you ask about my preference, I actually like this one a bit more. Okay, because just because it's a bit easier to remember. It's very intuitive, it's really similar, it's really just a mashup of, if you remember the second order videos and all, it's really just a mashup of what we had when we had complex roots, and also this case when we have repeated roots. Okay, when we have repeated roots, so that's why that makes it easy to remember. Okay, but if you wanna write it in the most concise manner, okay, obviously you can actually first write this, then simplify this. But if you wanna in your very first attempt, right from the get-go, write your solution in the most concise form, you can write it like this. Anyways, so the important thing, we really deserve some congratulations, because now we have the ability to solve any nth order linear homogeneous ordinary differential equation with constant coefficients. Okay, because we saw we dealt with any case that might arise with our solutions, or to the characteristic equation. If there's some number of distinct real roots, we know how to deal with that. It's this iconic term of ours. We need to do that for every real root, and then just add all of them. All right, if we have a real root that's repeated. Actually, yeah, I really should have emphasized the fact that this is a real root. Okay, so if you have a real root that's repeated k times, okay, what we're gonna have is something like this. Okay, the way I remember it is you have your general k minus 1 degree polynomial, k minus 1 degree polynomial in x, and then you multiply that by e to the power px. P is your p is your repeated root. And if you have complex conjugates, complex solutions come in conjugate pairs. If you have k such pairs, which means you have 2k roots. And actually, by the way, this was one thing I almost forgot, but we needed to verify. If you have 2k roots here, this needs to contribute 2k arbitrary constants here. So let's see if it does that. And in fact, it does. From C, all the C's, you have k of them, and all the D's you have k of them. Okay, so yeah, it's k plus k. That's why you have 2k arbitrary constants. So this is in fact a valid general solution. Now, back to topic. We can see that our solution we can write it like this. Just the case with the complex solution mashed up, with a kind of a mashed up version of that, and also our, what we have when we have repeated roots. Okay, but if you want to write your solution in the most concise manner, you can do something like this. So e to the power lambda x, where lambda is your real part of your repeated solutions. Okay, it has to be the same. Okay, multiplied by your inside, what you're gonna have is cosine of mu x, means imaginary part. Okay, either one of them. Okay, so that multiplied by if k is if you have k pairs of those conjugate roots, so you're gonna have a general k minus 1th degree polynomial, okay, multiplied by cosine. Also another different general k minus 1th degree polynomial multiplied with sine of mu x, and all of that is in brackets, because all of that is multiplied by this, the exponential. So that should be the end of this video. Okay, one last thing, I really should have mentioned this earlier when I was covering all this. Now, just like this second order differential equation video where we had repeated roots, I proved it at that time why this procedure works, but I didn't prove it here. Okay, why in general doing this works. Actually, the proof is a bit involved, so I'll probably make a separate video on that. Okay, so I won't be covering that here. So yeah, that should be the end of everything I have to say. So if you like this video, please do leave a like, please subscribe, keep studying smart.